Well, thanks everyone for coming. That's a little bit more people than I was expecting, so I have to be careful with what I'm saying now. This is joint work with Bob, who helped me a lot along the way, figuring out things that I need to figure out. And the entire motivation for this was to figure out what is it like to have a way to take seriously the idea that um, you have a program and it has some input and it does something. And at some point you get, oops, not in this order, an output and something comes out of it. And that's not really groundbreaking, but what is very useful to think about in terms of those programs is when you can write them like this, if you can bundle up the input and the output in a single unit, and then talk about those programs in terms of intermediate states towards other programs that have other inputs and other outputs. And once you think of it this way, you can start thinking about this entire back and forth as a single operation between this pair of input output and this other pair of input outputs. And let's say now we have um, a pair of inputs and outputs, and you have another one. Uh, what is it like to compose them to obtain an A to C? So what we're going to do is that we're going to treat those pairs of input and outputs as containers. And to quickly recap what a container is, we're going to define them as, um, well, I'm trying to think about different ways of phrasing this, but you can say it has a set of inputs and it has a set of outputs that are indexed over the set of inputs. So that means whatever you get out must relate to or relates to whatever has gotten in. Another way to see this is as a set of queries. So if you have a system and you want to ask something, you have a query, and from this query you get a response, right? And again, the response has to match whatever the query was. So this is how we're going to um, think about those programs as uh, interfaces towards interfaces between containers. And so what are the things that are here that convert between inputs and outputs? This is what is going to define, this is what is going to be defined by a container morphism. So in the typical case, if we have an input I and an output O, and we want to have a morphism with the inputs I prime and an output O prime, we define this as a way to forward translate the inputs. So that's an I to I prime, and a way to backward translate the corresponding outputs. So we have an X of I, and we have an O prime. So this says given an input X, and given that we ran the computer through our queries, we've obtained the response O prime, right? We obtained the response O prime here, and we need to translate this again into an O. So we've done this. We've done this round trip. So we've computed our thing forward. We found an I prime from which we obtain an O prime. Now we need to translate the O prime back into an O, knowing that the O corresponds to the X that we've given above. That's great. We can do things with this, but programs are a little more complicated usually than that, than A to B and B to C, etc. So the insight here is that there's a number of programs where this doesn't work and you want to do something else. And what I mean, this doesn't work, I mean that if you have an input here and an input, well, let's just go back to A and B. You can't just go from A to B because sometimes this fails. And what do you do when this fails? Look, the typical approach to this when you're programming, let's say you're parsing a string into a tree, you don't write this function, right? You write this function. You can say either get a tree from parsing my string, or I get nothing because something has gone wrong. The format was not what was expected. The string was empty. Some number did not end up turning out to be a number. There's formatting error, like some Unicode formatting does not work. Whatever it is, something has gone wrong. And composing this program is extremely important because most programs, it turn out, don't behave perfectly, predictably. So what can we do to solve this problem? We can think of this. So one way of thinking of this is we know that this is maybe A is like 1 plus A. If you think about containers, it turns out that we have a lot of monoidal structures on containers, including a coproduct. And we also have things that behave like neutral elements for those monoidal products. So is there such a thing as a container A to 1 plus B? And it turns out there is. So 1 is just, plus is just the coproduct on containers, and 1 is the neutral element for plus, which on containers turns out to be 1 and 0. And what this allows you to do is to write your computation in a string diagram style way where you can imagine your computation going there and then splitting into 2 bits. You have the case where your program goes with 1 and you have to do something, probably recover from the error. Another case where you have a value and you can keep going. And I'm not going to elaborate on the nature of string diagrams because I'm going to show examples now of how to use this. And I don't have a way to show off computationally how to execute those string diagrams. But what I'm going to show now is how to use this structure where this is seen as a monad on container and how you can compose those morphisms using the typical programming patterns that you use when you do monadic programming. So when you apply things like join, peer, or when you work in Kleisli category. So the most basic thing we should look into is this container morphism. I'm going to write it like this. So this is a container morphism that takes an A, and I'm going to write A again as this. And if we write the two functions that define the morphism, or the two mappings, the first one is quite easy to write, and the second one is also quite easy to write, provided that you know how to translate A's into A primes. Now this becomes, I should amend this. This becomes particularly interesting if you use A twice. So if A is simply the container A and const A, then this just becomes the identity, right? If we can hook this into some sort of program, that we wrote, let's say, C to B to D to A, and we have a way to close the loop with a unit here, we can use this to run an entire pipeline that goes through here, executes at A, and then rolls back into C. And what this will do is execute the program with interface C, program with interface B, D, A, and then reinterpret all the responses until we have a response that makes sense here. So what I'm going to show now is how this works in action, because we have a small, and my mouse is not working now, which is extremely distressing. I think it's this one. Yes. And let me just move this window away. Let's not start with this program. Let's start with the simpler one. Aha, I've already written the code here. So let's move this away for now. So I have here a program called main that is of type IO that calls this thing, which we're gonna look at the type right now. And what it says is if you have one of those container morphisms, then and provided you have some information about A and B, so A and B are the input and outputs of this container, of the left part of the container morphism, of the domain of the container morphism, then you can obtain an IO action. In particular, it means that if you can decode A from bytes and encode B into bytes, then you have a program. And the program we're going to run is the container we just talked about, which is the one which has on the left side the same thing twice, and on the right side a unit. So this is an identity. This is a identity function disguised as a container morphism. And if we run this, let me just do this. If we run this, we have a command line interface where if you write anything, you obtain the thing back. So we've turned our identity function into an interactive program where the operation performed on the input is the identity. Now this is reassuring. Like, we haven't done anything, but we also done something that works. Can we do more? And we can do a lot more with this. One of my previous work was about how do I combine and pipeline different parts of a server interface. So you have as input and outputs a request and a response, and server middleware, so pieces of software that will manipulate those request response pairs. And we can do the same thing here with this here. So if you look above here, I have another container morphism, which is defined with the composition of two container morphisms, parse operation and operate. So, and I'm just going to call this here. I need to get my cheat sheet. Ah, yes, because this is not the correct type. There we go. So run calc is a container that takes as input paths. So the questions that we ask are paths, and the response we get are integers. And it's a closed operation because on the codomain side it has a unit. You'll notice it has a maybe here, so that means that the operation can fail. And why can it fail? It's because here we have another container morphism that takes question answers of shape path and then anything, and returns as codomain possibly successful operation trees. So operation tree is literally just this data structure that says what operation are we doing and what are the arguments to this operation. And then operate takes an operation and executes it. Again, this is a this is dressing up a plain operation, a plain function that takes an operation and returns an integer. But we wrap it around this. We wrap it around the fact that we know things about container morphisms. Sorry, about monoidal operation containers. In particular, what we use for maybe, and maybe I can show this now. There we go. This is the magic sauce, which makes everything work. Maybe is applying the composition monoidal operation containers with the maybe container. And the maybe container is defined just above. It says if it has as questions booleans and as response evidence of truthness. Or if you think about those are data descriptions, this describes that we maybe hold a value or not. So by pre-applying the maybe container with using the composition operator, we obtain that either we obtain a value or there is an error and there is nothing we can do. And thanks to composition, basically, we don't need to deal with the error. The error is carried along the way we expect. So in case of errors, the error is just propagated. And again, we're using the fact that this, oh, I lost it. Sorry about this. We're using that this is actually turns out to be a functor on containers. Now, after defining calculation, we can pre-compose a calculation with another operation that we call parsing, and it does the same thing. This one never fails, so we're using plain container composition. And once we do this, I need to cancel this, run this again. I need to remember the format now. You can pass it a URL, well, a path, and it will parse it and extract the arguments for you and execute them. And there are only two operations we can do, and if you do anything else, it will just tell you something went wrong, right? Because the maybe case will be taken and nothing will happen. So that's not where it ends. This is literally just the beginning, because I said at the beginning this was chiefly motivated by my use of container morphisms for servers. And what I wanted to do, one of the things I wanted to do is see if we can write middleware for server, like give them a precise type for what it means to be a middleware and be able to compose them with existing servers. So what we're doing here is we're closely composing two container morphisms, one that does authentication and one that executes the calculator. And authentication is written just above. It takes a list of authorized users and says, are you authorized or not? So if you're authorized, you just go through fine. If you're not authorized, everything is canceled. So you go in the nothing branch of the maybe. And again, we can execute this. And now, well, okay, empty string is not splittable, but that's fine. So now the format has changed. You need to give a user and you need to give it a path for the calculator to interpret. So we've given two users to authenticate. It's Alice and Bob. So if I do Alice and then multiply 3 and 4, sorry, 2 and 3, I get something that works. But if I do John and I do plus 1 and 2, it says could not authenticate and then error. So what's great about this is that we've kept the same logic, we've kept the same program, run calculator, but we've added something in front of it that does authentication, and we simply compose those two things. And if I can show uh, this, so what we've done is we had our calculator, which takes a path and interprets an integer. Well, gives us an integer, and I'm gonna put it like this. This is our calculator. What we did is, wait, is it our calculator? Just a minute. No, it's not our calculator because our calculator takes strings and it returns maybe 1. So our calculator is like this. Our authenticator is like this. List user times string and int. I'm cheating a little bit, but I hope you can understand my intent. So given a list of users that are authenticated, oops, maybe. You can either succeed and then move the argument forward, or fail and then abort and go back. And we just use Kleist decomposition to say otherwise followed by calc is our entire program. And this way, we take the list of authorized users, the input, and then return the result of the computation. Okay, so that's the basic example of like an interactive program built out of containers using very simple operation on containers and their morphisms to build something that is extensible and interactive. We can take this a little bit further, where we can showcase. Let's see how we can use this to show the string diagram structure a little bit more and how this relates to existing lens-like operations. So let me change the screen a little bit here. Actually, let me do this. There we go. So on the left, I have two languages, a service level raw syntax for a language that would be something like the lambda calculus with let bindings. And down here, I have another language, which would be the lambda calculus without let bindings. And the question is, if we think of a desugaring operation as a question response mechanism, can we build a desugar that takes raw syntax and gets us a little bit more elaborated syntax? And what we do is they have this very simple container, which takes raw syntax and returns lambda calculus terms. And we define a couple of rewriting rules that will take syntax terms and return sub-syntax terms. So you see that rewriting a variable, for example, is one of those leaf rewriting rules. To rewrite a variable, you just interpret from the original raw syntax into lambda calculus syntax. There's nothing to do. To rewrite lambdas, you need to rewrite the body of the lambda. So we have a container that, let me write this on the side. This is why I have this. So we go from, for variable, we go from raw to units. For lambda, we go from raw to more, more raw things. And it keeps going, right? So for application, you start with the raw piece of syntax, and then you need to rewrite two more raw pieces of syntax. And finally, for let, same thing. You start with a raw piece of syntax, and you need to write two sub pieces of syntax right here. So with this, it turns out we can combine those. And can I show this? Yeah, so this is the tensor product on containers. So it does product on shapes and product on positions as well. And this is the coproduct here, which does coproduct on shapes and coproducts on positions. So with this, with what I have on the left, we can write a program that will take any arbitrary raw syntax and rewrite this into a smaller syntax. And we do this by writing the program that's down here, which is called rewrite all. And we're cheating a little bit because we're relying on the non-totality checking of iterates and our arbitrary recursion, but it does work. And what we're doing is that we have this container here called prism that's defined just above that will split apart our syntax and tell us which case we are looking at. So are we looking at a variable? Are we looking at a lambda? Are we looking at application? Or are we looking at a let? And depending on which one we are looking at, we're going to do different things. So if I write this as a string diagram, we have our syntax here, or it's called raw on the paper. It splits into 4 cases. And in the case of a variable, we're done. In the case of a lambda, we need to rewrite the body. So this is going to be a recursive call. In the case of an application, we have 2 more things to solve. So there's going to be 2 recursive calls. And for let, we're also going to have 2 more stub problems or 2 more stub pieces of syntax to solve. And this is what this code here is doing. It's doing the coproduct of all rewriting procedures given the coproduct of all possible constructors for the syntax. And then we obtain this, which is, again, as we established, this is a disguised function from raw syntax to lambda terms. So I don't have a demo for this, but we could write it now. However, I think we should go towards the next example, which is we've done an interactive program where you can ask or you can send requests and you get responses. And we've done one where you can send syntax problems and get syntax responses. This is one where you ask questions about JSON structures. So there is this tool called JQ, which allows you to take a JSON value and then perform some queries on it. And where is this thing? Here. So the structure of a JQ query is very simple. You give it JSON, you get a JSON back. The difference, the question is like, how different are those JSONs? What do you do with them? And there's a number of things you can do in a JSON file. You can abstract some fields from it. You can assume that it's an array and then get the nth element from it. You can modify some set fields of it. You can take a list of fields and then focus on the subpart of a list of field. We can do most of those operations, probably all, but I haven't done all of them because time. And I have an example here. So I've also tried to imitate the query style of JQ a little bit. So this is the identity query on JSON, well, on JQ input and output responses. So let's quit this program and call this one. And I should show the fruit file. So we're just looking at this JSON file right here. Oh, let me, sorry, you can't not be able to see it. Here. There we go. So we have a fruit file that contains an array with 3 fruits in it, and they have fields name, color, and price. And what we're going to do is we're going to perform the identity query on this. And we obtain literally the same thing, except you can see the format is a little bit different because I've put 4 spaces instead of 2 spaces, just to make sure that I'm not cheating, right? We are indeed reading the file, parsing the file, reprinting the file. It's not fake, right? What if we want to get the first element of this file? We can do the following. We have a container morphism that takes that takes a JSON value, assumes, well, tests for if it's an array, and if it's an array, obtains the nth element of it. And again, you can think of this as Clade decomposition, where is array is a morphism from JSON to maybe list JSON, and then get element is a morphism from list JSON to maybe JSON, and you need a natural number. So index JSON is the composition of those 2 operations. And again, if we run it, why is it taking so long? It doesn't usually take this long. There we go. We obtained the first element. Now the great thing with this is you've noticed that I've used something called view query, but we can also do run query. So this is the typical difference between a view and update in lenses, where one of them is, well, the view on the data, and the other one is the update on the data. So before we do this, you will notice this is composing 2 queries, right? Get the first element and then look up the field color. And if you run this, you get yellow, right? Because the color of the first element in the array is yellow. If we want to execute a query, we can do the same thing, but we need to give it a way to update the field that we focused on. So we've composed 2 queries and then said close the loop using this update mechanism. So close the loop means disguise one of those functions into a container, into a codomain of unit. And again, if you do this, well, okay, I've used grün, but oops, what happened? Let's use something that displays correctly, blue. There you go. You can see now that bananas are blue. So we did perform exactly what you wanted to perform in terms of lenses, but we've translated this into a string diagram-like operation by composing queries. Now here's the last thing I want to show, and that's how you can use this not just for asking questions about syntax, but you can, because we're using containers, we can ask more precise questions about where the heck is the thing? You can ask more precise question about a language and its proofs. And I need to find the container for this. Oh, it's right here. So we have this small language here about natural numbers, and we have a small equational theory using those natural numbers. And we're going to represent programs in this setting with a where the questions are pairs of terms, so pairs of things we've built with our well natural numbers we've built with our language, and their corresponding proofs. Uh, and here you will notice we're not working with just pairs of types, just like where before. Here we have a legit container uh, with a dependency between the response and the query. So very quickly, we have proofs that are reflexivity proofs, proofs by transitivity, proofs where proofs by congruence with successor, congruence with plus, symmetry, and then associativity. We could have written this any other way, but this has the nice way of thinking about goals and sub-goals. So specifically for associativity, what we see is that to obtain a proof of associativity, you have to solve those three sub-goals. So you have to prove that T1 is the same as T2, you have to prove that R1 is the same as R2, and you have to prove that S1 is the same as S2. And that your left-hand side and if so, then this left-hand side has the same, is the same as this right-hand side, or rather, it's a valid proof to assume that they are. As you remember with the desugaring example, we have leaf proofs. So here, REFL is a leaf proof where you have no subgoals. Transitivity has two subgoals where you need to prove the first part of the intermediate step, and then from the intermediate step to the right part of the equality. Congruence has one subgoal, which is the proof with that successor, etc., etc., etc. So we're building containers out of those. So here's the first one. This is our leaf container. So it takes an equational problem and says we're good to go, or rather, as long as everything's good, we can keep going, or rather we're done. And again, this is the maybe container composed with the unit container. In particular, it means that if this input on the left is not provable by reflexivity, we get nothing out. Same thing with, same thing, sorry. Transitivity, we can see here, we said transitivity has two subgoals, right? One for from the code, from the left part to this intermediate problem, and then from the intermediate to the right part of the equation. So we just need to give the intermediate term, and then we need to solve two further subproblems. And associativity is a big one. So associativity takes one equation problem and returns possibly three subproblems. And what we can do now is that we can we can use those as a language to write tactics to transform problem solution pairs into sub-problem solution pairs. And we can also use those to write custom tactics. So here I have, and I'm going to go back to showing this. We have this signature that says we have a custom tactic that's a leaf tactic. And what it will do is it will perform those steps, but they're a little bit hard to read in this way. So what I'm going to do is I'm going to write those as a diagram on the left so we can follow. So the first thing we're going to do is we're going to perform symmetry. So if you have A and B, this is going to turn into B and A. Symmetry creates two subgoal, right? It takes, it doesn't create two subgoals. Symmetry just does not change the goal. It just transforms it from one shape to the other. The other one we need to prove is associativity. So associativity takes two things, and then you need to prove that they are um, they are like you need. Okay, well, let me maybe this is not the correct way to do it. Uh, we have let's start over. We have this tactic A plus B plus C, uh, where A and B and C are separate, right? This is our associativity tactic. We want to check this one, however, we want to do the opposite one, A plus B plus C. We want to ensure that this is the same as C, as A plus B plus C. So there is a little bit of work to do, and what we're going to do is apply associativity, but precompose it with symmetry, and then there's more work to do in order to fix up the fact that associativity returns units, because this is actually going to end up into three other proofs that needs to say that those things are the same. And so what we do is we take this, we flip it into uh, C, A, B, and then we use, so this is symmetry, and then we use associativity, and then we to prove that A and C, B and A, and then C and B are the same. And then we do this by reflexivity. And that gives us the type from 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 problems to units, because now we can collapse all those units into one. And here's the test case. It works. Unfortunately, it's just at the type checker level, so it's not as fancy as the other ones in the command line. But again, you could run this in the command line if you had enough infrastructure. And I think that's it for the demos. Yes, so I don't have any more demos, so I'm technically done, but there are more things to talk about. So if anyone has questions, we can stop here and ask questions.